the week 4. So before we start, maybe you can conduct a survey. So to know how well you understand the topics. So just a quick survey. So I think that these are the few topics we covered last week. And so just give a score. So today we'll be covering the forward kinematics. So the forward kinematics will basically be based on the homogeneous transformation matrix. So if you understand the topics from last week, then the forward kinematics will be just a summary of all the configuration frames. So I think most of you have already understand what is the orientation of the robots and the position. And to sum all these two up is the homogeneous transformation matrix. So around 3. So before we start, is there any questions you want to ask? If you have some any question that concerns you about the last week topics? So I'll leave this page. So if you have any question, you can just leave your message and I will read it. So today we come into the position analysis. So it's the forward kinematics. So we'll explain what is the forward kinematics of the robots. So this is the topic. So these two are the introductions. And from last week, we started to get to a mathematical modeling of the robots, which is the homogeneous transformation matrix. So to use this mathematical method, is the forward kinematics. So what is a serial manipulator? I think most of you have already known what a serial manipulator. A serial manipulator consists of several links connecting a series by various type of joints. So if the robot is connected serially, so this is called a serial manipulator. One end of the manipulator is attached to the ground, and the other end is free. So we can also call this type of robot is the open loop, or a serial manipulator, or serial robots. So the other hand, this one, the n effector, is free to move in the space. So a serial manipulator is something called open loop manipulator. So you can see this is an open loop. And we call the fixed link here is the base. At the other end, here is the end effector. So if they have a serial manipulator, so there will be a parallel manipulator or a closed loop manipulator. So if a robot let's connect back to the base or form a closed loop, this will call a parallel manipulator, or we can call a closed loop. So this is an open loop. So basically in this lecture or in this module, we only cover more on the serial manipulator rather than the parallel robot. So this is a typical serial manipulator. So this is the relative angle between the links and the following one. So the first link is here and the second link. And the relative angle between the two links is the relative joint. So this is the joint angle number one. So if we have a prismatic joint, so this is the relative position between the two links. And usually we can describe using the theta 1 to describe the relative joint, and D3 or EI to describe the prismatic joint. So what we want to do is to describe the n effective post, the frame, based on the reference frame. So this is what we want to do. Because it's like when we're controlling a robot, what we can input is theta 1, theta 2, theta 3, and theta n, and D1, D2, Dn. So this is our input. So this is we can control it through the motors. But what we want to do is we want to know where the robot's n effector is X, Y, Z, and the orientation. So this is what we can input into a robot's motor, and this is what we want. We want to know the place or the configuration of the end effector of the robots. So we want to know this frame, based on respect to the base frame. So this is a scoreboard. You can see that here is the base, and this is the link joint 1 is the regular joint, and here is the link 1, and here have another regular joint, is joint 2 and link 2, and joint 3, link 2. So on both. So the n is the n effector. So when controlling a robot, what we want to know is the position and the orientation of the n effector based on our base frame. So this is what we want to know to solve this robot kinematics. So for the robot to perform a specific task, the location of the n effector relative to the base should be established first. This is called the position analysis problem. So it's like all the robots are built up by several joints and several links. And what we want to do is we want to know where is the n effector, so we can control it to do our task. So there are two types of position analysis problem, the forward and the inverse. And we will explain it later. So for the forward kinematics, the joint variable are given, and the problem is to find the pose of the n factor. So for the forward is we have the reading of the motors, and we want to calculate the pose of the n factor. And for the inverse is reverse. So for the inverse kinematics, the pose of the n factor is given. So this way is forward, and backward is inverse. So the problem is to find the joint variables necessary to bring the n factor to a desired location. So you may think like if we want to grasp a cup, and we know the x, y, z, the position of this cup. So we want to control our robots to this position. So what kind of kinematics we want to use? If we have a desired configuration we want to go, so what kind of kinematics we need to use? Any answer? Forward or inverse? So it's inverse, because this is we know the position of this cup, and we want to know what is the degree of our motors, so we can reach this position. So this is the inverse problem. And for the forward problem is that we already know the motors readings, then we want to calculate the pose of the n factor. So to summary, we can use this diagram to see. So we have a joint space. The joint space means that we have inside is all the robot joints, the joints values, the theta 1, theta 2 to theta n. And we have another one is the Cartesian space. So the Cartesian space means that it's in the XYZ space. So the forward kinematics is transferring the joint space to the Cartesian space of the n factor. And the inverse is backwards. So any question of what is the definition of the forward and the inverse kinematics? So today we are covering the forward kinematics. So we are given the joint value, the motor's joint values, and we want to calculate the pose of the n factor. This is for today's lecture. So we can use this equation as the forward kinematics. This is forward kinematics function. And the R means the configuration of the n factor. So here is the base frame, and here is the n factor frame. So we want to know the R. So the methods for computing this function, there are two types. One is using the geometric. So we are teaching both methods to you today. The another one is using the homogeneous transformation matrix. So we'll start with the geometric. It's through by inspection. But usually can only do for really basic like planar manipulators. If you have like 3D manipulators, then by inspection may be more difficult. So if we have a two-link robot, so maybe we can have the zero configuration here. So this is the length 1 and length 2. So we have two regular joints, and we have two links. So we have theta 1 to describe the first regular joint, and theta 2 to describe the second regular joint. And what we want to know is this one, the position and orientation based on the reference frame here. So we can know that for R, we have Py, Px, Py, and the theta. So for planet, we have 3 degree of freedoms, have 3 variables, is x, y, and theta. So by these 3 variables, we will know that the configuration of this n factor. So this is for the first two one. The first two will be the position of the n factor, and the last one, the theta, we will know the direction of the n factor. So how can we map this theta 1 and theta 2 to Px, Py? So this is the following kinematics problems. So the input is theta 1 and theta 2. And output, we want to know Px, Py, and theta. So I think most of you have known that we can describe by using the trigonometry. So it's like so if this one is the link 1, and here is theta 1. So what is the position? Here is 0 and y and x. So what is the position of this one? What is the position of this one? If this have theta 1. So it's cosine, it's L1 times cosine, I'll use the white. L1 times cosine, theta 1, and L1 times sine, theta 1, and the orientation here, right? So this is this direction. So if we have two links, here is theta 1, and the extension of the link 1, and here is theta 2. And now what is the position and orientation of this point? So there's L1 times cosine theta 1 plus L2 times cosine theta 1 plus theta 2, right? And for the y, it's also and for the orientation, it's theta 1 plus. So this is because if we are using these x, and here is theta 1. So we have theta 1 plus theta 2 times the L2 to get a position. So through this function, we can transform the theta 1 and theta 2 into the px, py, and theta. So here is px, py, and theta. So this is called the forward kinematics. It's transferring the joint value to the n factor pulse. So if we are, so for a scenario, if we given like theta 1 is equal to 0 and theta 2 equal to like 90 degrees, if we have these two inputs, then we will know that the n factor will be at this position, which we can compute the position and rotation of the n factor. So we will know that if we given these two inputs, our manipulator will go to that position. And this is a typical, like, I think this one is 1, 2, 3, 4, 5. With the 5 degree of freedoms robots, and this one is a 6 degree of freedom robot. But if we want to use the inspection or the geometric method to conduct on the like 6 degree of freedom robotic arm, then it will be very, very difficult. So through a geometric method, usually we will only use partially or only use by like pipe, very, very easy manipulators, then we can use through the inspection method. So normally, what we want to, how we to solve the forward kinematics is using the transformation matrix. So the first step, so we need to recall from the last week assessment. The first step is that we need to assign all the local frames at each joint. Can everyone recall from the last week assessment? We assign the local frames at each joint. So after establish all the frames, the local frames at each joint, we can calculate the relationship between the adjacent frames. And then we have the homogeneous transformation matrix. Then we times all the homogeneous together, the matrix together, then we will get the n effective frames with respect to the base frame. So can you recall from the last week assessment? And for the last week assessment, we want you to assign Z as the joint axis, direction of the joint axis, and X you can assign whatever you want, and then the Y is computed by the right hand rules is Z to X, so the Y is here. And I know this is quite difficult. You want to make sure what is the orientation to rotate X when rotate about X, rotate about Z. So after setting up these frames, you will need times to write down the correct homogeneous transformation matrix. If you still can recall from last week, our homework. So today we want to teach you a method that you can assign the frames, and directly from the frame you can get your homogeneous transformation matrix. You do not need to rotate about x-axis and y-axis to matching the two frames. So this is called the Dennenberg-Kahlenberg method. So it's introduced by these two famous, I will say, is mechanicists. So Dennebeck and Hardenberg introduced this convention in 1955 to standardize the coordinate frames for spatial linkage. Because before then, we want to assign, I think most of the researchers assign the frames, the local frames by themselves, and they need to check the orientation every time. So then Dennebeck and Hardenberg, they introduced this method to standardize all the frames. And there's a method that directly generates the transformation matrix based on the 4 parameters. So these 4 parameters are called the DH parameters. And to have these 4 parameters, you need to set up the DH conventions. So afterwards, we will teach you how to set up the DH conventions, and from there to get the 4 parameters. So the 4 parameters are the D, and alpha, and theta, and the last one is A. I think here is using the. So these are the DH convention rules. How to set up the local frames. So from the last week, we already tried that all the z-axis should be collinear with the axis, joint axis. And so this is the first rule. The z-axis must be the axis rotation for rubber joint, or the direction of motion for prismatic joint. So the first rule, I think most of you are very familiar with that. So it's the same as the last week. So the second rule is the axis must be perpendicular both to its own z-axis and the axis of the frame before it. So what that means? So if we have, this is z and x, and here is y, 0. So if we have a joint over here, we know that the z1 axis should be collinear with the axis of the joint. So this is z1. And the x-axis must be perpendicular both to its own z-axis and the z-axis of the frame before it. So the z-axis is here. Before it, z0 and z1. So we have a lot of direction we can choose. So on this frame, on the xy frame, it's because these two axes are in the same directions. So I think all the direction if you choose on the xy plane can satisfy with this rule. And the third one is all the frames must follow the right-hand rules. And these are extra rules. So it's the x-axis must intersect the z-axis of the frame before it. So we know that the z0 is here. And the x-axis is some direct direction over here. And we want to intersect the z0. So this is the direction of the x1. So we will intersect the z0. Is this okay? And this also satisfies with that the x1 is perpendicular to a z1 and z0. So it's perpendicular. And it intersect with the z0. And after we establish the z-axis and the x-axis through the right-hand rule, we will know that the y-axis is over here. So follow these 4 rules. This is the DH conventions. So maybe we can try it for a few examples. I think the first one is the same. This is z0, x0, and y0. So we know that the z-axis must be collinear on the x direction, and the x must perpendicular to the z1 and z0, and y can be generated by the right-hand rules. And we can check whether the x-axis intersects with the z-axis. So this is how we set up the diagram for the first one. So the second one, this is z0, x0, and y0. And we know that there are two directions we can use. Maybe we can just use whatever you want. It's the same, but I'll choose this direction. So the Z1 is pointing out of the board, and we want to know the X. So if we choose the X direction at this one, X1 is perpendicular to the Z1, and it's also perpendicular to the Z0. So it satisfies the second rule. And through the right-hand rules, we know that Y is pointing upwards. And we check the fourth one. The x-axis is intersect with the Z0 axis. So this logo frame also satisfies the DH convention. And now we see the third one. So this is a prismatic joint which can move in this direction. So the Z0, X0, and Y0. And we know that the z-axis must be in the direction of the motion of the prismatic. So here is z1. So the x must be perpendicular to the z1 and z0. So maybe we can choose here x1, and from z to x is y1. And now we want to check whether this x-axis is intersect with the z-axis, and we found that they did not intersect because x-axis is here and z-axis is here. So what should we do? So the method is that we can move this frame to this point. So become Z1 and X1. And here is Y1. So the method is moving the frame to satisfy that the x-axis intersect with the z-axis. So I think we have done all the techniques to set up the diagrams. So the revolute joint, the joint axis, the z-axis should be at the joint axis, And for the prismatic joint, the z-axis must be in the direction of motion. And now we come to how can we get the DH parameters. So this is a typical joint, a typical link with two joints, joint I and joint I plus 1. And in this lecture, we introduce you to use as the standard DH parameters, DH method. There is a modified DH method. I think it's in the J.J. Craig book. But in this lecture, we introduce the standard DH method. There is some very, very slightly difference. So in the standard DH method, this joint axis is Zi minus 1 at joint I. So there's the z-axis at joint I is Zi minus 1. It's quite confusing, right? But this is how it's set up. So joint I, the z-axis at the joint I is Zi minus 1. And the z-axis at joint I plus 1 is Zi. So there's 1 plus 1 difference between the joint number and the axis number. So the four DH parameters is measured is the D, theta, and A, and alpha. So through these four parameters, we can describe the two relative coordinate frames. So the A is the offset distance between two adjacent joints, axes. So this is joint I axis, and I plus 1. The A is the offset distance between the two joints axes. And the alpha is the angle, the twist angle between these two axes. And afterwards, we'll teach you a method to get these four parameters. But here is just lets you to understand what is the geometric meaning of these four parameters. And the D is the translational distance between the two incident normal of the joint axis. So usually the incident normal of the joint axis, what is called, is usually the link. Usually, but not always. Because sometimes the link will be like not in the straight lines. So usually it's the link. So you can probably say that this is the translation distance between the two links. This is the joint axis, and this will be the two links. So if we recall from the earlier, we said that if the translational distance change between the two links, what is the joint of that time? So we have two links. So the distance between these two links changes. What is this type of joint? Anyone? If the distance between two links change, what is this type of joint? So this is link I and link I plus 1. And it can move to become something like the distance becomes very large and also become very small. So this kind of joint is the prismatic joint. So B is usually the variable of the prismatic joint. And the theta is the angle between the two links. It's the incident normal of the joint axis, but we can just simply say it's the link. So if we have this is the joint axis, and here is the theta. If this theta changing, what is the joint time of this joint? So it's revolute, right? It should be a revolute. So we can change the angle between the two links. So the theta is usually the variable of a revolute joint. So these are the 4 parameters of the DH method. So it's from link I -1 to link I. And we measure the joint time. So these are the 4 parameters. So to summarize, I think these are too difficult to read. So we'll just skip it. And this is just a summary that for revolute joints, A, alpha, B are constant, and theta is a variable. For prismatic joints, A, alpha, theta are constant, and B is a variable. I think we have already introduced this from the last slide. So we can just see this, the words inside this red bracket. So what is A? You can just follow this sentence. And here is the example here. So AI is the offset distance between z-1 axis and the zi axis along axi axis. So what is the z-1 axis over here? It's the z0, right? And the zi axis is v1. And along the xi axis is along the x1. So z0 is here, and z1 is here. So the alpha is an offset distance between these two axes in the direction of x1. So it's this distance. Is this okay? Because it's z0 and z1, the offset distance between these two axes in the direction of x1. So here is A1. Is it okay? And the alpha is the angle between the zi-1 axis and zi axis about xi axis. So here is the z0 axis and z1 axis rotate about the x1 axis. And because the z0 axis and zi axis here are in the same direction, so here for this one, the alpha 1 is equal to 0 because they are in the same direction. And the number 3 is the D. It's the offset distance between x-1 axis and the xi axis along zi-1 axis. So it's the x0 axis and x1 axis along z0 axis. So we will calculate this axis and this axis along the z0. So this is E1. Is it okay? You can just follow the sentence, the words. And for the theta, it's the xi minus axis. It's x0 and xi axis is x1. Rotates about z0. So it rotates about this axis. So it means the joint. So for theta 1 is theta 1. This is a variable. Because if we we can imagine that the x1 axis is rotate about the z0 axis. So this one is the variable. In this configuration, it's 0, but this is the variable of this joint. Is it okay? The other three are constant number. So the other three are constant. And this is the variable. So we get the DH parameters. So this is just an example. You can just put into like I-2 for the I. So I-1 is 1, I is 2. So just follow the sentence and get the angles. And we'll have a short video to introduce.
To look at Herrenberg parameters, the right is to simply describe the motion of a series of voltage joints. This is useful for efficient calculation of forward and inverse kinematics. The process begins by defining the z-axis along the axis of rotation for equilibrium joints, or the axis of translation for prismatic joints. Since this is the first joint, the x-axis is the free choice. For later joints, each x-axis will point away from the previous joint. The y-axis simply completes the right-handed reference frame. Now, if we add another joint, we can determine the transformation between them. As before, the z-axis points along the axis of rotation. The dH parameters will be derived from the common normal between the z-axes. The common normal is orthogonal to both vectors. It's also the shortest line between them. The new x-axis points along the common normal and has its origin at the intersection of the new z-axis. Notice the origin is not within the physical actuator because the dH parameters are only concerned with the motion of links, not the physical placement of the links. Using this protocol for laying out the reference frames, only 4 parameters are needed. The first of these, d, is the depth along the previous joint's z-axis, from the origin to the common normal. Theta rotates about the previous z-axis to align the x-axis. R is the length of the common normal itself. Most texts call this parameter A, which is unfortunately easy to confuse with alpha. Instead, calling it R is used for the moment, as this is also the radius of revolution for the new origin about the previous z. Finally, alpha rotates about the new x-axis to move z into alignment with the axis of joint motion. Now there's one special case in the z-axis of parallel. Because parallel lines have an infinite number of common normals, you can choose any d value you like in order to place the new origin in a convenient location, such as the center of the link or the tip of the net effector. The other parameters are the same as before. Theta rotates about z to align the x-axis with the normal. And R translates out along the normal to reach the new origin. Alpha is already known to be 0 in this case, since the z-axis must be parallel for this to apply, thus no rotation is needed. Congratulations, that's all there is to it.
So this is a very short video that can have visualized what are the 4 parameters. And if you are still not very familiar with these 4 parameters, and you can just follow the summary of how to find these 4 parameters. But to have these 4 parameters correct, your DH convention must be set up correctly. So you need to follow the 4 rules to set up the DH frames. Okay, so maybe we can take a break first. So after that, we can come back to you for some examples. So I think most of you have still remember for the transformation matrix, so which one doing first? Is a prismatic or a rotation? Which one happens first? Is a translation first or rotation first? One or two? From the last week. So it's the first one, right? So the first one is a translation. So we start with the D. So the z-axis will conduct first, then the x-axis. So z-axis will conduct first. So we'll have D. So in the first, so we can separate DH parameter into 4 homogeneous transformation. It's the 4 parameters: the D and the theta and A and alpha. So the first one, the I-1 coordinate system is translated along the z-1 axis, a distance di. This brings the origin OI-1 into coincidence with HI-1. So it's here, the OI-1 to the HI-1. So the difference, the translation difference between these two x-axis along the z-I-1 axis is the di. So the corresponding transformation matrix, we can write it as this one. Okay, so here make the mistake, here should be 1. I'll change right now. Okay. And the second one, we know that we need to do the z-axis versus the x. So just now we have already computed the translation. Then afterwards, it's the rotation, so it's the theta. So we know that the theta means that the xi-1 and rotates about the zi-1 axis to the xi. So this is theta. And it's also, it's the geometry form, meaning it's also the joint rotation of this joint height is the theta. Because these are two links, and it rotates above this joint axis. So it's also the joint angle. So we know that from the last week, we know that the rotation about the z-axis is cosine, sine 0, and minus sine, cosine 0, 0, 0, 1. So this is rotates about the z-axis. If you still can remember from the last week orientation. So, so before doing this kind of DH method, I really like to let you understand what is the meaning of the rotation matrix before directly going to the forwarding mathematics. So if we see this rotation matrix, we know that it rotates theta degree above the z-axis. And the third one is the A, it's here. So this is the distance between the two z-axes, the zi-1 and zi. So it translates the A along the x. So we know that it translates A along x. So it's as the A, the x projection. So this one is x, px, py, and pz. If you still remember from the last week, the position or translation part. So we know multiply this transformation matrix means that we will have AI translate AI distance along the x-axis. So we come to the last one, is the alpha. And the alpha means that it's the rotation, the angle between the two z-axes. about the x-axis. So this rotates alpha about x. And through this rotation matrix, we know that it rotates alpha I value about x. And the position does not change. So if we multiply all together, the transformation matrix for the DH parameters is D times theta times A times alpha. And the sequence should be in order. We also know that if you multiply randomly, the answer will not be the same. So we must multiply in order. And this is the general form of the DH method. So for like a typical robot, if you set up your DH conventions and you get your DH parameters, then you can directly substitute the parameters into this homogeneous matrix. Then you will get the relationship between the two frames. So this is the DH transformation matrix. So you have these four DH parameters: the theta, alpha, and D, and A. So these are the four DH parameters. And usually, this is from the base, so it's usually the base is 0, but here we put it into difference. But usually the base, these are two equal, and the A means that we have a lot of links, n links between them. So the A is also used as T, the transformation matrix, and we have the input is theta 1, theta 2. Get to the theta n. So we will have all these transformation matrix, and we have the input data. So by these two, we can get the configuration of the n effector frame based on the base frame. So this is the description inside the robot. So inside the robot, it's using the data, because inside the robots we only know all the values of the motors. It's by the data, the degrees. And from the external, we want to know is the XYZ, the position, and also the direction. And let's try. So this is 3 arm manipulator, planar manipulators. So follow these rules, and let's fill up this DH table. So maybe you can try it. So normally when we see a robot, this is a random configurations, and we need to set a 0 configuration. So it means the initial configuration of the robot. So if we want the easiest one, it's maybe just let it to line into a straight line. Or you can set this one as a 0 configurations. What does the 0 configuration means? Or the initial So what is the zero configuration of the initial configuration is? Anyone? What is the meaning of this? It means that the input theta 1 is equal to 0, theta 2 is equal to 0, and theta n equal to 0. So this is the configuration, or you can say the pose, that all the theta is 0. So it means the zero configuration, or the initial. And there is the zero configuration is by your definition. So I can say that my zero configuration of this robot is going straight up. So this is zero configuration. If I set all the motors value to 0, so the robot is in this configuration. So this can be by zero configuration. And also we can set this configuration as zero configuration. Any pose we can set zero configuration because we can set our motor to 0 value at any point. So the first thing is that we need to decide which one is our zero configuration. So if we set zero configuration beside this means that at this point, all the theta is 0. So if we set zero configuration as this one. And we know that the z-axis must be on the axis of the joint. So it's pointing out. And we can set the x and y and x1. And we check the z-axis is here. So the x1 axis is perpendicular to the z1 axis and z0 axis. And it passes through the z0 axis. It intersects with the z0 axis. And by right hand rows, v and to the x, so the y1 is here. And also, we can get the x2 and y2. The last one is the any factor frame, is the x3 and y3. So like this, we can set up all the DH convention. And after you set up, you need to check with whether you follow all the DH convention rules. So now we can follow the definition. The A1 is the offset distance between the Zi-1 and Zi axis along x-axis. So it's the Z0 axis and Z1 axis along x1 axis. So Z0 axis is here, Z1 axis is here. So the offset distance is here. So it's A1. And along the x1. So we can get this A1. And the angle between the Z0 and Z1, because they are in the same direction, so it's 0. So we can have a DH table. Then it's alpha, A, and B, and theta. It's 1. Because 1 means that it's 0, I-1 to 1. So here is I-1, 0 to 1. So alpha 1 is alpha 1. And alpha is 0 and A1. And we can see the D. D is the offset distance between x1, x0, and x1 along the Z. So they are in the same line. So there's no opposite distance at the z-axis. So it's 0. And the theta is the angle between x0 and x1. So if we see that if this angle moves theta 1, so here will be the x0, and here will be the x1. So if they move a variable of theta 1, the angle difference between these two axes is theta 1. So we know this one is the variable, and we can write the variable in different colors. And because all the conventions are the same, all the frames are the same, so we know that they will be the same. Is it okay? Because all the frames are the same, because all the relationship between them should be the same. Is it okay? So then we can substitute all these 4 parameters back to the DH general we just substitute all these parameters back to the DH general transformation matrix. So we can get this 3 matrices. And we can check whether our transformation matrix is correct. If just now, if you recall from the geometric method, we know our Px is equal to A1 cosine theta 1 plus A2 cosine theta 1 plus theta. And for Py is equal to A1 sine theta 1 plus A2 sine theta 1 plus theta 2. For the theta is theta 1 plus 2. So if you recall this, so we can check whether we have the same because just now we only have 2 links, so we can multiply these 2 together as A02 equal to A01 times 1 A2. So it's C theta 1 and it's A1 cosine A1 cosine theta 1 A2 sine. I think we don't have enough space, so maybe we can write it the second one here. So we multiply these 2 together, and we can get the first one is cosine theta 1 sine theta 2. So you can check this one is equal to cosine theta plus theta 2. If you check the first elements, and if we check for the px is the fourth one, so it's cosine theta 1 times 8 2 cosine theta 2 minus sine theta 1 times a2 sine theta 2 and plus a1 cosine theta 1. So these two can combine as a2 cosine theta 1 plus theta 2 and plus the a1 cosine theta 1. So it's matched with our geometric method. So through this, you can check whether your answer is correct. Is this okay? You just multiply these two matches together, then see whether the px is the same. Is it okay? Or we can have more space here to check. So we multiply these two metrics together. So we check the px. So px is equal to cosine theta 1 times a2 cosine theta 2. So plus, and it's minus sine theta 1 times a2 sine theta 2. And the third is the 0, and fourth is plus a1 cosine theta 1. So we can have these three. So these two can combine together. If you still remember cosine theta 1 times cosine theta 2 minus sine theta 1 sine theta 2 is equal to cosine theta 1 plus theta 2. If you still remember this geometry formula, so we can change this one into a2 cosine theta 1 plus theta 2 and plus a1 cosine theta 1. So it's equal to. So this is px. And we can get the same answer as our method using the geometry method from the previous slides. And this is a scalar. Wow. So the first joint is a revolute, second joint is a revolute, and third joint is a prismatic downwards, and the fourth one is also a revolute. So it's a 4 degree of freedom robot. So if you align the joints in this sequence, it's a scalar. So a scalar robot is R, R, P, R. If you align your joints in this sequence. And it's usually used in the industrial to do assembly. Because unlike 6 degree of freedom arms, you can have different orientation. A scalar robot can also only have one data rotation. So we can move x, y, and z using the perspective. So this is the scale round. And let's build a DH parameter for this scale round robot. So the first thing is that we need to determine what is our zero configuration. So if we line this camera into a plane, and we can determine this one as a zero configuration. So if you see in the figure, this joint axis is bending quite a bit, but we can straighten up to be as our zero configuration. So after that, then we need to assign a base frame. So we assign Z0 and X0 and Y0 as the base frame. And remember our rules for the DH convention. The Z-axis must be in the direction of the gravity joint axis. So here, this is the Z1. And the X-axis must be perpendicular to Z1 and Z0. So we can still set here. And the y-axis, it can be determined by the right-hand rules. So the y point. And we need to check. So the x-axis is intersect with the z0 axis. So this frame satisfies the DH convention. And the third one, we know that the z-axis must be in the motion of the joint. So whether you want to go up or going down. So here we choose going downwards. So this is z2. And we know that the x should be perpendicular to the z2 and z1. And so we set in the same direction. So it's here and to x. So the y should be pointing out. And we check whether the x2 is intersect with v1. So it's in the same, so they intersect. So if you extend, they intersect at this point. And the fourth one, we need to, so the joint is here, so it's V3. And then we can check if we have x3 over here and y3 is the same. And we check whether the x is intersect with the z2, x3 is. So you can extend the z2, this is the line, so it's intersect with the x3. And the last one will be an effective frame. So maybe we set here. So this is Z4, and we just copy it. Because usually the an effective frame will just duplicate the last one. Because if there are any, only if that's your tooling, if your n effector have defined configuration, or else we will just duplicate the last one. So we do not need to do more calculation. So this is one. And now we need to find out the DH parameters. That's alpha I, AI, BI, and theta I. So 1, 2, 3, 4. So now we follow the first one. The alpha I is the angle between Z0 and Z1 about x1. So the Z0 is pointing upward, Z1 is pointing outward, so they are in the same direction. So alpha 1 is 0. And A1, it's a Z0 and Z1 along x1. Z0, Z1 along x1. So it's this distance. And D is the distance between x0 and x1 along Z0. x0 to x1 along Z0. So this is D1. And theta is the x0 and x1 about Z0. So if you remember that for perimeter joint, theta is the variable. And because they are in the same direction, so you do not need to add anything. And for the second one, alpha is the Z1 and Z2 about x. So Z1 is pointing upwards, and Z2 is pointing downwards. And x is here, so if we rotate about x, then we need to rotate pi degree, or pi for radian, or 180 degree. So this one is pi. And A is Z1 and Z2 along x2. So here is A2. And D is the offset distance between x1 and x2 along V1. So there's no any offset distance because they're in the straight line. So we can get the D is 0. And for theta 2 is the x1 and x2 rotate about Z1. And here we know that x1 and x2 are in the same direction, so the difference is 0. But this one is the variable of the joint 1. So we don't have it's the variable of the joint 2. So it's theta. And we can check the number 3. So the alpha is a Z3 and Z2 about V3, X3. So Z3 and Z2 are in the same direction. So the alpha is 0. And A is the Z3 and Z2, the distance, the difference between them. So they are in the straight line. So the D3 is, the A3 is 0. And the D3 is the X2 and X3 along Z2. So X3 is here, X2 is here, and along the Z2. So here is D3. And if you remember, this one is a prismatic joint. So here we have a variable. So the D3 is a variable. And the theta is the difference between the two x. And it's 0. And because this one is a prismatic joint, so here we don't have the variable. And for the fourth one, the alpha 4 is the Z4 and Z3. And they are in the same direction, so it's 0. And for the A, it's Z4 and Z3 because they are in the same line, so there's no difference between them. And the D4 is the X4 and X3, and this is the difference between them. So here we can say it's D4. And because this one is not a prismatic joint, so this is a constant. And we will have the last one is the X4 and X3, and about the Z3. And we know, because this one is a rubber joint, so we know the theta 4 is a rubber joint. So by this, we already set up the DH parameter of the scalar robot. So the next thing we need to do, so why there's a half of pi here? Do you know why? What's the difference between these two conventions? So if you see the base term here, the x is pointing outwards, so y is pointing in this direction. But our setup, our x is pointing this one. So this is why we will have a half a pi difference from here. So if you set up your frame differently, then your DH parameter will be different. And if you set up your zero configuration different, of course your DH parameter will be different. So we just plug in all this DH parameter into our general equations, the matrix. Then we can get the 4 transformation matrices. And if we multiply the from 0, 1, 1, 2, 2, 3, and 3, 4, then we can get the configuration of the n effective frame respect to the base frame. And what if we want to get the position of the joint form, or the position of joint of link 3? What if we want to get this one? How can we get a position of this? So we know that so the relation between these two are 0 and 1. So this one is 0, 1, 2, 3. And 4. So if we want to get the 1, we can just refer to this one. And if we want to get this one, then it's A02. So equal to 0, 1 times 1, 2. And if we want to get this one, it's A03. So it's so the last one. So it depends on which joints you want to find the position or the rotation. You can choose the transformation matrix you want to multiply. So we can get this 4 you can say 5 because this one is the base, so it's 0, 0, 0. And the first one, and the first joint, the position of first joint, second joint, third joint, fourth joint. You can get the transformation of that from just multiply the transformation measurements. And there's another example. This one is a scoreboard. Just as you have seen the image of this robot. And we can have a very fast try. So first, we need to determine what is our zero configuration. So maybe you can set up as the joint 1 and the joint 2. So it is, there's a small offset. A small offset. And then there's another revolute joint, and followed by another revolute joint. So this is the joint 1, joint 2, 3, 4. So then we will have a 5. So the 5 is in the same position. And the angle vector. Okay, so now we want to set up the pH parameters. So after we already assigned the zero configuration, now we want to assign the frames. So it's Z0, X0, and Y. Then we can follow Z1, X1, and Y1. So it's the same. V2, X2, and Y2. And Z3, X3, and Y3. Because it's all the same, so we can just duplicate the frames. So the fourth one is the fourth one is different. So we know that the Z-axis should be pointing forward. And then the X needs to be perpendicular with the Z3 and Z4. So Z3 is pointing upwards, and Z4 is pointing forwards. So the only direction left for the X3 is pointing out of the road. X3. Sorry, it's X4. And we can check ZX, so the Y is pointing down. And 0, we can check whether the X intersects with the Z3. Because these two are in the same point. They are in the same point. So then of course this one, the X equal intersect with the Z. And then the last one, we can have the Z5 and X5 and Y5. Just copy this one. So we can set up all the frames very fast and without we don't. So you can still remember from the last week your homework or your assessment. You need to compare like these two whether they are rotating about which angle, and just like if these three are the same, but if you want to change from this one to here, you're thinking that maybe we want to rotate about the y-axis. Okay, it's just rotate about the y-axis. But through the DH methods, you do not need to compare the rotation by yourself. You can just follow the rules. So we have the alpha, A, B, and theta. So the first one, the alpha is a Z. It's a 0. And the offset of the Z is this one. So maybe we can use anyone. B is the X between these two along this Z0. So here is B1. And theta 1 is the variable. For 2, the Z-axis, this is the angle between two Z-axis, it's 0. And offset between these two is A2. And between the two X is 0. So, sorry for that. I think I made a mistake because the Z-axis should be pointing outwards. So, okay, I made a mistake. Sorry for that. Enjoy it, okay? So the Z-axis should be pointed outwards. And X, we can have it here. So Y is pointing upwards. And we can check whether the X is intersect with the Z0. So okay, then we can follow Z2, Z3, and this is X2, Y2, and X3, X3, Y2. And then it comes to this one. So again, we can, the Z should be pointing forward. So Z4. So we have Z3 pointing outwards and Z4 pointing forwards. Right? So the only left direction for the X is pointing upwards. So the X3, X4 is pointing upwards. And then the Y is pointing forwards. And we can copy duplicate the same trend. Okay. So we need to redo the DH frame, the parameters. So maybe we can have a break. So I'll finish the parameters. You mean pointing inside or outside?
Outside.
Inside. So pointing inside and outside is you can choose by yourself because it's in the same direction and just affects the negative and positive of the value. 上礼拜做的业务其实不需要去用编曲，你只用点轴下来是其实没说，因为就是因为他做不到自己方面的事情，那既然有自己的东西，你长怎么知怎么设，然后一直说你自己要走上大家比较懂的点，可是有时候你在想我要 Excel 上，你不是说不行，但是你就变成自己创造规则，但是因为在列出来之前的话，其实大家都是你怎么说的更好，那只是说大家可能会知道说，哎，你的字就是在 Excel 对，所以这个，所以它其实没有什么真的或没有在市场上做。对，因为被编辑表示会发现你完全没有在比这些东西，对，可是你自己都比出来，它没关系的话，市场就不会有问题。对，因为它关系就是你写出来的，然后我就没有，对吧？所以这样子来讲，是用这个，对，其实如果你要 rate 可以啦。对啊，只是说怕大家搞混，因为我是听那个罗老师说那个下学期的语境老师开的是，对，然后但是我知道罗老师还是说要对，给我们那个对，他这样的明白，但是其实都差不多，就只是说你去看他就会。So after I can check with the our slides, you can find that we have one negative sign difference on the slides, and you can check the convention over here. So you can see the x is pointing forwards and y is pointing downwards. So in this convention, x is pointing forwards is the same, but y is pointing upwards. So that's why we have a minus sign difference over here. So the other will be just the same. So, any question about the DH method? Back to our so you can type in the menti.com and use the code up here. It's 54503956. So if you have any question or comment, you can leave it here. And we have already uploaded today's homework to the Moodle. So if you have any questions, you can ask here, or you can just come up, or you can raise your hand. And for today's homework, we have 3 problems, but basically it's the same. It's the same. So this is problem 1. So you use the data sheet provided in the next page. This is the FANUC industrial robots, and all the link parameters is over here. And you sketch a sketchmate diagram first, and assume that the 0 configuration is figure B, is this one. So you can assume that in this configuration, it's 0 configuration. And then you assign the local frames to each joint. So following the pH convention. So you can just review the 4 rules of the pH convention. And then you determine the corresponding DH parameters. And then from your DH parameters, you can derive your forward kinematics of this robot, and you can verify the result through the MATLAB. And afterward, I'll show you how to verify the results. And sorry, this one is problem 3. So problem 3 is you just given a joint vector, and you substitute this joint vector into your forward kinematic solution, and you can calculate the n effective pulse. The pulse means the position of rotation, so basically it's a homogeneous transformation with respect to the base rate. So you know that this robot at this joint values, what is the pulse, what is the position and rotation of the n effective. So through this, you'll successfully build a mathematical model for this industrial FANUC robots. So after you complete this homework, you can just try to like this one is joint 1 and joint 2, 3. So when a given joint vector to you, then you will know what is the position and rotation of the frame. So this is the forward kinematics. So you can start with your homework, and if you have any questions, you can leave it in the dashboard, or you can just raise your hand. I will come to you. I think it's just you are not familiar with this matrices. If you are familiar with this matrix, I think the forward kinematics is very simple, because the inverse kinematic is very hard. So because today the forward kinematic is you just multiply all the matrices, then you can get your results. But the inverse is you need to use the one matrix to find all the joint angle, and inverse is much harder than the forward.